Okay. Listen, thank you guys for coming today. We're going to start on time. We have a lot of things to do today. If you weren't here for the pre-show talk a minute ago, my name is James. I'm the chief meteorologist for ABC 3340. I have a small part in this today, but we have a lot of things to do, and we will be cognizant of your time. We thank you for your willingness to spend a Saturday with us. Very quickly, we'll do the logistics here. The first thing we do today, Brian Peters will be training the basic Skywarn training. I know that many of you have done basic training. Many of you have not. So we're going to go through that. I encourage people to get a refresher course every year. And then after the basic session, Kevin Laws, who is the Science Operations Officer for the National Weather Service in Birmingham, will do a presentation called Polygonology, which is absolutely fantastic. So we're looking forward to hearing from Kevin. There'll be a very quick lunch break, and lunch is on your own. And by the way, we are going to do a Song of the Night meetup, and if you don't know what that is, don't worry about it. That's a little niche group we do on the late news at night, but we'll do that at lunch. After lunch, I'm going to come back and do a little presentation on lessons learned after April 27th. We're coming up on the 5th anniversary of the generational tornado outbreak. We're still reeling from that. A lot of you know I had nothing to say about it for 6 months, and even today the words come hard, but I'll be talking about that. And then Brian will end this with the advanced session, and we'll do our best to get you out of here by mid-afternoon. And after this is over, everybody here goes to the car show free, which is fun. It goes on here at the same venue. I know a lot of you came a long way for this, and I'm thankful that you're here. This is an amazing crowd for a Saturday. But before I bring up Brian, I want to introduce Charles Daniel. Charles is the morning meteorologist at ABC 3340. The man has the hair of an angel. Nobody should have hair like this. I think it's either a toupee or a weave. We're trying to figure that out, but Charles gets up at 1 o'clock every morning, and he doesn't sleep either, and he does this long enough, he'll wind up looking like me one day.
I was just telling everybody that if I try to get more sleep than James just so my hair doesn't fall out. But if I was going to buy hair, it wouldn't have all this gray in it. That's the key. So more and more. Plus, I have twins, if you didn't know that. I'm originally from Atlanta. My family's from North Alabama, and this is where my wife and I have been for the last 10 years. We just love this area. This is where I want to be, and this is home to me. I feel a lot more connection to our family here than anywhere else, and we're just glad to be here. I'm going to take a second here. Who's been to church and when it's really crowded on Easter Sunday and they're like, all right, everybody scoot to the middle. I'm going to do this because we're really filling up very quickly. If there's an empty seat in the rows, if you guys could just slide to the middle. I know these first few rows are just packed full, but that way some of the stragglers coming in, they'll be able to get on the outside without having to scooch over you like in the airplanes or something like that. That's a little too close for comfort there. But if you could, and if there is an empty seat nearby, if there's any singles over here, raise your hand and just kind of point to that. That'll help fill in some of these seats up front. All right, so if you guys take a look, that's good. One of the reasons we do this also, we always talk about severe weather, and this is what this is about today, but also we're going to let you become one of the Skywatchers, so you can become that Skywatcher program. And a lot of you guys are here today, and what helps us, even just on those regular days, we get reports like, oh, it's 57 degrees in Center Point. That's good. We get reports like 57 degrees, 52 dew point, partly cloudy skies with a light southeasterly wind. That's really good. That tells us what's going on in these localized areas because there's only so many sensors around. And then when storms come, you got eyes out there on the sky. We can see, we can relate, and you guys can help us. It's difficult sometimes for us to see exactly or know exactly what's going on without eyewitness reports because we're stuck in a studio. Let's face it, it's hard sometimes for us to really be able to say this is what's going on there, especially when we get light rain or virga, something showing up on the radar and it's not really coming down. And then snow events. A lot of times this really light snow we get, not even coming down. And you guys are out there telling us, well, I got a few flakes. So it really helps out in that situation. Twitter's always a great way to contact us, so make sure you fill out these forms and stuff. And Megan will be handling that. She'll be contacting you. Did she make it yet? I know she was trying to park a little while ago. No? Okay. She's somewhere in downtown trying to park. She'll be here in a little bit to say hey, but she'll tell you more about that as the morning goes on. We really appreciate you guys being here and all that you do, all our Skywatchers, and all of you that are going to join that program today. We do appreciate it, and God bless you guys for being here. Thank you.
All right. So, again, First off, it's going to be Brian, and then Kevin Laws. Brian, for those that don't know, he's been with us for at least, 12 years? 12 years. Brian worked for the National Weather Service in Birmingham for many years. He was the WCM, the Warning Coordination Meteorologist, and this is part of what he does. It's trained. So, again, we'll do basic training, and again, I know a lot of you have been through it. I encourage you to kind of focus in, because it is so easy for us to think, well, I know all that. Listen, as I get older, I've learned how much I don't know. And so I learn something every time Brian speaks. So we'll have Brian come up, and then after Brian, we'll have Kevin of the Weather Service, then we'll have a quick lunch break. And my first question, and the only question, and you know what it's going to be, does this man look more like Colonel Sanders or Santa Claus? All right? It's not Christmas. I'm thinking the Colonel. So, ladies and gentlemen, Brian Peters.
Do I honestly have to say thank you? Okay, I got a couple of questions for you all. I don't know if you were at Tuscaloosa. Anybody was at our Tuscaloosa training? Okay. Well, if you were there, you know what happened in Tuscaloosa, right? I had the youngest storm spotter ever. She was 6 weeks old, okay? Well, we have another first here this morning. You're not going to believe this. On the front row, we have newlyweds. And we got entirely too much information about what happened yesterday, and they got married, and then and they're here this morning, and they had to get up early. So, just goes to show things can happen. I'm curious about something very quickly. Anybody in the audience who would consider themselves a first responder, whether it's police department, volunteer fire department, EMT, anything like that? Okay. Wow. Okay. That's great. The thing about first responders is that a lot of times first responders are out there, period. I know in my tenure with the National Weather Service, we relied heavily on police departments, law enforcement in general, sheriff's departments, highway patrol, law enforcement, because they're always out there. And oftentimes they're the only reports we get. So Charles was mentioning how important your reports are, and they really are. Now, before we get started truly, I have a tradition that I've done at this particular venue for the last several years. Anybody been to this venue before? Okay, well, some of you know. You have any idea what's coming next? Okay. Well, I've done a lot of work on finding out exactly who James Spann really is. And it's been a very interesting journey going through all of this. So this is the way that we see him on the blog, okay? There he is. There's James. But around Halloween, he likes to enjoy his favorite costume. Anybody know what this costume is? Are you ready? This is an iPod.
Brian needs some new material.
Ditto. Okay, but and this morning he really outfoxed me. He didn't tell you that he's been on television since the Civil War, right? Okay, well, that's all right, because we've gone into some very top secret information to find out exactly what James has been doing over the years. And he bills himself as a bit of a scientist. Oh, yes. He's been studying how to hear airplanes for a long time. And there he is working on one of his experiments. But that's not the only one. He's tried several things. We tried bugle type things to hear. And then there's even another one. This is one of my favorites right here, trying to focus those sound beams in. And then, of course, this has got to be one of my favorites right here. There he is. I especially love the position with the hip, and it's got to be great. But, James is like all of us. He has aspirations, right? I mean, we all have aspirations, right? Well, one of his aspirations is he really wants to get up there on the space shuttle and the ISS. But he found out something. We had a meeting with the NWA back in 2011 here in Birmingham, and James got to talk with one of the people that had been on the space shuttle, and he talked about a problem. It's called bloating, and this is what happens when you go up into space. Well, James still went up. Unfortunately, he was affected. Now, just recently, the government opened some secret archives. So we were able to go and see these new images. And indeed, it's absolutely the truth. He was forecasting the weather in the Civil War. And we actually have a photograph to prove it. There it is right there. There's James. You know, he's not in front of the green wall here, but, you know, he's getting ready to do the weather. And then, of course, if any of you watch the blog, you know about the infamous voodoo country, right? So we have voodoo country. Well, Yoda was not the first one. Okay? So there's James. Okay. Yes, and he's definitely got to get some new material. All I can say is chicken for everybody. Okay, now let's get serious. It's pretty interesting, this atmosphere that we have around the Earth. The atmosphere is actually this little bit of blue that you see right here. See how the white line is the top of the clouds, basically, and then you got this light blue that goes all the way up here. And you notice it gets thinner up here. It's true, the atmosphere is thinner at the poles than it is at the equator. It's about 100,000 feet thick. But the question I want to ask you right now is why? And that is a very important question to answer. Why are you here? That's one why. Why do we want you to be here? That's another why. Why do we need you? That's another why. And those have an answer. And this is a slide that was put together by a friend of mine at the Norman National Weather Service office. And this, to me, pictorially, and I found out a number of years ago I'm a very visual person, so it helps to see things. I still can read, but it helps me to have pictures to learn how to do things. And this really says it all right here. Radar is a tool as a meteorologist that I definitely will not want to be without ever. I would never want any meteorologist facing a severe weather episode to have the radar be down. It's an absolutely fabulous tool. But the problem with radar, and there's always a problem even with good tools, is it doesn't show us what's happening at the ground. It shows us what's happening above the ground. Now, as I say, it's a great tool. We went from just standard radar that was deployed in '57 to the Doppler system that was deployed in the late 80s and early 90s. And with the Doppler system, we now could see how the water droplets were moving relative to the radar, either away from the radar or toward the radar. And that velocity, we began to see all kinds of couplets, that is, rotations that existed in thunderstorms that we had no idea were going on before. As a matter of fact, within a week of turning on the first Doppler radar in the state of Alabama, which was the Maxwell Air Force Base. It's not actually located at Maxwell Air Force Base. It's over near Tallahassee. Within a week of turning that on, actually I think it was 4 days, we actually saw our first velocity couplet. And bless his heart, the meteorologist on duty, I don't blame him a bit. He was scared to death to issue a tornado warning based on the velocity couplet because we'd only seen them in training. And so a severe thunderstorm warning was issued initially, but that was later upgraded to a tornado warning when we began to get some reports. The truth is that it is only storm spotters that can see down at the ground. You know, when the radar beam is sent out, it is basically, it's not absolutely perfectly straight, but you can think of it as being straight. And as it goes out, the Earth curves away from it. So the beam is getting higher and higher and higher. And so the problem is you get out 60 to 100 miles and you're beginning to get 5, 6, 7, 8,000 feet above the ground. So we're not seeing down low. So when we see a rotation and the rotation is up here at say 8 or 10,000 feet, we're not sure that this is happening. And this is why we need storm spotters, because the ground truth adds so much to what the meteorologist is seeing. It adds confidence to warnings. If we're seeing a rotation on there, but we have no reports, we don't know that that thing right there is occurring. So your reports really do help. And I want to give you a firsthand account of a situation that did occur. This is a true story. On April 27, 2011, I was storm chasing, and a colleague and I, we were on the western side of Jasper, near then it was future I-22, it's now I-22. And we observed a small thunderstorm come over us, and underneath that was a rotating wall cloud. Not very big. The cell itself on radar really wasn't that impressive. But we called that report into the National Weather Service in Birmingham, and they issued a tornado warning because they had a rotation in that cell, and they had a ground truth report, so they were very confident. Now, that cell did not produce a tornado in Walker County. But what county is just to the northeast of Walker County? It's Cullman. The first tornado of the afternoon was that cell that dropped a tornado in the southwestern part of Cullman County that eventually went on to hit the city of Cullman. How many deaths were there in that tornado? None. Absolutely. Why? Because the warning system worked exactly the way it was supposed to work. So your reports are especially important to this whole process. And believe me, they get into the system and they are part of the process. Now, storm spotting is dangerous. There's no doubt about that. If you've been on Facebook or YouTube recently, you may have seen the video that was taken back in 2015 of Fairfield, and I can't remember if it's Illinois or Indiana. It's one of those. It's Illinois. Okay. Fairfield, Illinois. I'm just heartbroken to see that because the gentleman is on the second floor of his house, and he's observing and filming a tornado that is approaching his house. And what does he do? Nothing. His wife is downstairs. There is no communication between him and his wife. His wife was killed when the tornado hit their house, and he was seriously injured. I mean, the video is fabulous, but for what purpose? Somebody had to die for that? That video it's not worth that. So I want to keep you aware that what you're doing is dangerous. This is the vehicle that 3 storm chasers died in Reno, Oklahoma. Back a few years ago, the El Reno tornado. And I did not, I had met him, but I did not know him very personally, but the head chaser in this group of the 3 was a slightly older guy, younger than me, so I can't call him old, but he was very much conscious of storm chaser safety. As a matter of fact, within storm chaser community, he was very well known for safety. And yet what happened? The tornado did something that he wasn't prepared for it to do. Did not expect it to do it. It made a slight curve, and it caught them, and they ended up, as a result of this, being killed. So keep in mind that it's very dangerous. We need the reports, but we do not want you risking your life. What we're going to talk about today is tornado climatology for Alabama. Some of the characteristics of tornadoes, storm structure, visual characteristics that you and I can see, storm safety, and if you last through to the end, we have some video to try to put it all into motion. It doesn't matter what year that you take and look at the statistics in Alabama. This happens to be 2002. Again, the year is not that critical, but we have these kind of severe weather events, all of which can produce fatalities. But the number column here shows you something. We don't have relatively that many tornadoes. We had 243 thunderstorm wind events. We had 222 large hail events. We had 51 lightning events that were recorded and 35 flash flood events. But you notice where the death toll was the highest? And now all you have to do is think back to April 27th, 2011. 252 deaths in less than 24 hours. 62 tornadoes. The sum of the tracks of those tornadoes, 1,100 miles, if you added them all up. So the problem is that tornadoes can be the most dangerous. Now, in many years, you'll be surprised, I think, to know this, but in many years, heat and cold will exceed hurricanes and tornadoes combined in terms of deaths. The problem with heat and cold is it tends to sneak up on us. These events, most of these events are what we consider to be short-term, just fast happening events. But tornadoes are the ones that can be the worst. But even though they can be the worst, there can be a lot of damage. This is an example of a hailstorm. Believe it or not, this was Arizona. I never thought you would need small craft advisories on a pool. But look at what the hail, the hail is really frothing it up there. We're also seeing a lot of damage coming from the trees with little bits of the ends of trees coming off, and there's a little bit of wind associated with it. I don't believe the wind was at severe limits. By the way, a thunderstorm is severe if it produces winds in excess of 58 miles an hour or hail 1 inch in diameter or larger. That's the size of a quarter. So hail can be pretty bad. We're going to look at a couple of different hail events, and I want to make sure that everybody knows. Let's see, that can do a lot of damage. Look at the splashes that are occurring. How big's that hail? It's a little hard to tell. Hail can be in huge amounts, but we want to know about hail sizes. That's very important. And the best thing to do is to report relative to coin size or to well-known subjects like tennis ball, baseball. Coin sizes, 25-cent piece is good. And if you take pictures, please get a nice reference like your hand or an item, like throw a quarter next to it or something so that you can get a perspective. And that will help out a great deal. When I first came to Alabama in '89, one of the very first severe weather events that I worked, a sheriff's department dispatcher called and said that they had large hail. And it's like, okay, could you be a little more specific? What's large hail to you? And there was this pause on the other end of the phone, and the lady came back and said, roughly the size of hen egg. And it's like, well, that's great. I wanted to ask so bad. I had to bite my tongue. I wanted to ask, is that small, medium, or large eggs? And hen eggs, not bad, I guess, but hen eggs do vary, so known sizes really helps communicate. All right, there's a number of rotations in the atmosphere. There are dust devils, gustnadoes, waterspouts, and tornadoes. What the heck are all these things? We're going to concentrate on that bottom one, the tornadoes. Dust devils basically start at the ground and work their way up. They are basically the development of thermals, updrafts, upward moving air, that for some reason, some shear occurs that causes it to spin. But as you can see, like this picture over here, you can see there's a good deal of dust or debris at the ground, but as it goes up, it fades out. They can go up a couple of thousand feet. They can be very ferocious at the ground. They don't usually kill people. You do not want to drive your car through it unless it needs to be sandblasted, okay? Because it will be sandblasted. The thing about dust devils is, whoops, sorry, it shifted. Rotations that go up, they fizzle in clear air. They're not attached to clouds. They're found mainly in deserts, and wind speeds in dust devils are on the order of 60 miles an hour or less. Now, if you really want to research this, you ought to go on YouTube and search for Hey Devil or Hey NATO. There's a great video from Vermont of a dust devil in a hay field, except there's no dust. So it's all the hay that's blowing around, and the video shows the kids running through it. So you can tell it's not very powerful. A gustnado is kind of complicated here because it actually does begin at the cloud base. It tends to be around the edges of a thunderstorm, generally on the leading edge, where we have the shelf cloud or roll cloud, we have the gust front. And what's happening is that you're getting, for some reason, you're getting a rotation that is on this gust front, and oftentimes they'll be like this. There'll be debris, but there's a connection here. So it does actually begin within the clouds, just like this one. We've got our debris here. We really don't see much of a condensation funnel because it's not as much condensing in this area. So it does begin within their weak rotations. They are connected to the cloud base, so they are sort of similar to tornadoes. They are not linked to thunderstorms. You may have them with a simple shower that has a nice gust front. They're relatively shallow as opposed to tornadoes, which tend to be much deeper. They're created by shear along that gust front. So are these tornadoes? Well, if you report one, it will get reported as a tornado, but they really aren't in the classic sense of what you and I as storm spotters can look for. Now, if you ever go to the beach, always be on the lookout for a waterspout. Waterspouts are essentially tornadoes over water. They do begin within the thunderstorm or within the cloud. They do not have to have a thunderstorm. They can come out of what's called a towering cumulus, the development of the updraft prior to it actually developing rain or thunder. And again, we don't have to have thunder with them. The interesting thing here is if you look, especially on this one, you can actually trace how the air is moving. The air is coming in like this and coming around and around and into and then up into the waterspout rotation. So in the case of water spouts, they can come out of towering cumulus. There's often no lightning or thunder. Yes, they can move ashore, and if they move ashore, they then become tornadoes. They are basically would become a weak tornado as they move ashore. One of the reasons why we have quite a few of these we have quite a few tornadoes reported in Mobile and Baldwin County is that several of those were waterspouts that came ashore. Even for a brief time, they basically are still considered to be tornadoes at that point. But we're going to focus on the classic tornado. Tornado is defined as a violently rotating column of air in contact with the ground. It's nothing magical or mystical like the Wizard of Oz. It's just air. It's air that's rotating at speeds that vary from as low as maybe 60 miles an hour in some of the weakest ones to wind speeds that approach 300. We really don't know the exact highest wind speed in a tornado because as damage occurs, it occurs at the weakest point. And so we don't really have any good measurements. And most measuring equipment, like weather observation sites, when they're hit by a tornado, they do what? They blow away. So you have nothing left. So the bottom line is we have to resort to remote sensing. Remote sensing is like radar. Now, the University of Oklahoma has developed something called a DOW, as opposed to the movie Twister that had a COW in it, okay? It's a DOW, which stands for Doppler on Wheels. And what they do is they put a Doppler radar on this big truck, not quite an 18-wheeler, but something a little smaller than that, but pretty heavy duty. And they drive it around, and they drive it within close proximity to a thunderstorm. They set the radar up, and then they scan the radar, scan the thunderstorm with the radar. The bottom line is there's been two observations, one in South Dakota and one in Oklahoma, where they measured, I believe it was in South Dakota, 284 miles an hour, and in Oklahoma they measured 315 miles an hour. Now, all these measurements were made above the ground, around 700 to 900 feet. Now, what we know about the atmosphere is that, of course, it's thickest at the ground. So as you come down, if you have 315 miles an hour at 900 feet, you will not have 315 miles an hour at the ground. You will have something less. But the point here is that with remote sensing, we basically have figured out that 300 miles an hour is not completely out of the question in a tornado. Now, what makes a tornado visible? Well, it's a combination of things. This one illustrates it quite well. We have primarily the clouds or condensation that make the funnel visible, and then when you get down near the ground, we have debris. This one, we're not seeing much in the way of debris. This one, we have a problem. We have an obstacle. We have some trees. We really can't see where it is. It's pretty sure it's on the ground. But this one, again, shows you the basics here. We've got a wall cloud. We'll talk about what that means here in just a few minutes. But the condensation funnel is here, and the debris is here. And there's a connection, even though it looks like there isn't. There is a connection there. Now, how a tornado looks is going to depend on a number of factors. This one is very well lighted. If there's ever been a photogenic tornado, this was one of them. Because if you looked over here, just to the south of this supercell, to the south, there was clear blue sky. So what was happening, and this was taken around 5 o'clock in eastern Arkansas, what was happening is the sun was beginning to set. It was in clear weather out here, so the light was coming in under the base of the thunderstorm, and while the base of the thunderstorm was very dark, it was lighting the tornado quite nicely. So we had great lighting. In this case, we don't have nearly as good a lighting, and up here we have pretty good. It's pretty well backlit. The problem, of course, with night spotting is you can't see anything. As a matter of fact, one of the people that I trained in when I was with the National Weather Service was only a half a mile from the April 8th, 98 tornado in western Jefferson County near Concord. And he told me that he was within a half a mile of the tornado, and at no point did he see it. He heard it, but he didn't see it, and he was that close to it. So at night, you have a real problem. Tornadoes come out of thunderstorms. I can't remember what that word was. Oh, they move with the thunderstorm. My apologies. I had updated the slides because of the James Spann slides. So they travel from southwest to northeast. And tornadoes come out of thunderstorms. So when a tornado occurs, it travels with the thunderstorm. It does not move in radically different directions. If I'm a thunderstorm and I'm producing a tornado and I'm moving this way, a tornado is not going to move that way. It's going to move with the thunderstorm. Now, typically in the spring months, the airflow above the southeastern U.S., the movement of thunderstorms, and therefore if those thunderstorms produce tornadoes, will be from southwest to northeast. In somewhere around the middle of May till the middle of June or so, we often get a northwest to southeast airflow. And when that happens, if a thunderstorm occurs and if it produces a tornado, the tornado will move from northwest to southeast. By the same token, in sometime in the end of June, July, and early August or so, we sometimes find ourselves in a flow pattern that allows easterly flow. So we actually get the thunderstorms forming east of us and moving towards the west. If one of those produces a tornado, it's going to be moving from east to west. It's not going to move in a radically different direction. The tornadoes will move at the speeds of the thunderstorms, which can be as low as about a standstill to as high as 70 miles an hour, and the 70 miles an hour was measured in Mississippi. So we know in the southeastern U.S. they can travel pretty quickly. As a matter of fact, on April 27th, many of the thunderstorms were traveling at 60 miles an hour or slightly higher. And wind speeds can be anywhere from 60 miles an hour in the weakest to wind speeds over 300 or up to 300 miles an hour. By the way, I want to address the idea of a thunderstorm that's not moving. We don't get many of those in the southeastern U.S., especially in the spring, because we usually have a really good airflow over the southeastern U.S. that's going to keep thunderstorms moving very quickly. In the case of Oklahoma, Texas, Kansas area, they often experience some dry lines, and they can get some supercell thunderstorms that actually move very little. If you have a supercell thunderstorm that is not moving, let's just say it's not moving, the mesocyclone, the rotation of the updraft, will actually be enough that it can actually, if it forms a tornado, the tornado may actually travel in a circle. But the condition is that the thunderstorm has to be stationary or nearly stationary. We just don't usually see that in the southeastern U.S. Now, we do have a tornado problem in the southeastern U.S. I'll address that in a second. Before 2011, Alabama and Arkansas used to kind of flop back and forth between third and fourth in terms of the number of tornado fatalities since 1950. And we use 1950 because reasonably good weather records on tornadoes have been kept since 1950. One of my pet peeves, as you've probably heard before, is when people refer to Tornado Alley. I do not like the term alley. I think of an alley as being a small, narrow path between two buildings. That's what I think of as an alley, okay? This hallway might be an alley, but I don't think of an alley as being all of the central and southeastern United States. So I just don't like that term. And I can back that up with every one of these is marked with an arrow is a southeastern United States state. We've got Alabama, Mississippi, Arkansas, Tennessee, Georgia, Florida, Louisiana. Did I miss any southeastern states? Okay, I'll concede North and South Carolina because maybe they are southeastern states. Maybe they're not. So the bottom line is out of the top 15 in terms of tornado fatalities, 7 of them are in the southeastern U.S. So the bottom line is we do have a tornado problem. If you look at the tornado records that have been kept since 1950, and again, we use that number because before 1950, there are records on big events and big tornadoes, but there's not much on other tornadoes because, for one thing, the population, say in 1950 in Alabama, and I keep meaning to look this up, but I figured the population in Alabama in 1950 was probably about 1 million, maybe, over the whole state, whereas today we're probably between 4.5 and 5 million. So we have many more people in the United States. I honestly do not believe that in 1950 there were only 2 tornadoes in the state of Alabama. Okay, I just don't think that happened. But if you look at all of these records and you start trying to draw a line to match how the tornadoes have been developing, you can kind of draw a line that's fairly flat, but then it starts to go up here, and then it just really goes off the the scale. Oh my God, it must be global warming! Where's the buzzer? No, it's not global warming. There's a lot of reasons for this. One reason is I've already mentioned. In 1950, the population was low. Now, the population is much higher. What does that mean? Well, what that means is it's really hard for a tornado to occur somewhere in the state of Alabama and not affect somebody or their property. So we're getting more and more reports. Also, something happened right about here. Anybody know what that was? Doppler radar. Absolutely. Yes, we got some scholars on the front row here. And Doppler radar came into Alabama in 93. And what happened when Doppler radar came in is, as meteorologists, we would issue warnings, and we would look at the radar, and we would see these couplets, and we would be over. And is there anybody here from Coosa County? Okay. Well, my apologies to Coosa County in advance. So I've used Coosa County because I have a good example. I'm not picking on Coosa County. We had one particular day at the Weather Service in Birmingham, we had a warning out for Coosa County, a tornado warning. We had an absolutely spectacular couplet. I mean, it was just well-formed, high values. I mean, it was just great. We issued a warning, nothing, no reports. Well, I'm sorry, but Coosa County is probably one of the least populated counties in the state of Alabama. So the next day, a colleague and I said, you know what? There's got to have been something that occurred out there. So we got in the car, and before we left the office, we plotted where the velocity couplet had traveled. So we drive over to Coosa County, and we're driving north, and I said to my colleague, I said, are we about to cross that path pretty soon? And he said, oh yeah, you're going to make a kind of a lazy curve, a lazy S to the right, and then it's going to lazy S back to the left, and we should be there. So we make the lazy S to the right, we make the lazy S to the left, and all of a sudden, on both sides of the highway, there were trees down. And I don't mean just a tree or two. I mean, there were trees down. As a matter of fact, there were so many trees, it actually had blocked the highway because somebody had come in and chainsawed the trees to get the highway back open. So the bottom line was, somebody knew about the damage and it never got reported, okay? But because we knew where the couplet was, we went out and we discovered it. So what happened there is in the early 90s, reporting gets a whole lot better because when we had the time and have the time, National Weather Service folks will go out and do some searching, and oftentimes we will find tornado tracks that never got reported by someone else. And when we get, well, I'll tell you right now, interesting thing occurred in March of 1994. You may remember the what is termed the Piedmont tornado. It's kind of a misnomer because it really didn't hit the city of Piedmont, but it killed 20 people at the Goshen United Methodist Church. What's really interesting about that particular tornado is that there were 83 tornado reports that were called in to Calhoun County 911. Fabulous. How many of those reports reached the National Weather Service? 0. Absolutely. It was after 1994, it was after that I began a very concerted effort to make sure that 911 offices knew we don't need all 83 reports, but the one that's most important to us is that first one. And we really need that. Now, I have to say that the National Weather Service office staff in Birmingham had issued an excellent warning for Cherokee County, which is where Goshen United Methodist Church is actually located. The warning was out actually 12 minutes before the church was destroyed. Unfortunately, due to church activities, nobody in the church ever heard the warning. All right, when do tornadoes occur? Well, there's peak season is March, April, and May, so we're sort of almost coming up on the middle of it, and April is our big month right here. And then we have a secondary season that's primarily in November, but it may begin in very late October, like maybe the last week of October, and it sometimes extends into the first couple of weeks of December. You may remember the December 2000 tornado, December 16th, in Tuscaloosa. That was one of the latest in the year in terms of violent tornadoes. Now, we do get tornadoes in all months, so we can't be complacent when we're not in the peak season or the secondary season. But the good news here is that it is the peak season and the secondary season when we get primarily the EF3s, 4s, and 5s. So the most violent tornadoes come in these two seasons. They're not exclusive. We do get a few here, and we may get something in December. But generally, in the fall, in the winter, the summer, and the early fall, all of these tornadoes tend to be rather weak. So while we may see them, they are weak, and September sticks out just a little bit because we have also the peak of hurricane season. And if we get a dying tropical system that comes ashore in northwest Florida or the Alabama and Mississippi coast, it has a tendency to produce some weak tornadoes within the hurricane circulation or the dying hurricane circulation. And so we have a little bit of a peak here that stands out because of the hurricane season. All right, so we know that tornadoes occur in all months of the year. What about time of day? Well, just like time of year, we have peak hours roughly from about 11 o'clock in the morning till about 8 o'clock in the evening. Now, again, just like time of year, we have tornadoes in all hours of the day and night. But one of the ingredients that really helps out is to get heat energy. And we get heat energy, of course, from the sun. Well, the sun rises here at 6, 7 o'clock in the morning, and the sun begins to heat the atmosphere. That helps to get thunderstorms rolling, and as thunderstorms develop, they begin to produce tornadoes. The sun continues to heat the atmosphere, so that helps the development of thunderstorms and helps the intensity of thunderstorms. So they begin to really take off here, and we get many more tornadoes. And then around 5 o'clock or so, we begin 5 to 6 hour, we begin to see the sun start to wane as the sun is dipping lower on the western horizon, and the number of tornadoes and the number of thunderstorms dies off, and then we finally get out of what we consider our peak hours. Just like for time of year, most, not all, but most of the strongest tornadoes are going to occur in the peak hours. But again, we have tornadoes in all hours of the day and night. I almost don't want to show this slide because I think it's kind of misleading, but we'll talk about it real quickly. This is the number of tornadoes by county, and if you add them all up, you'll get many more tornadoes than Alabama's ever had, because tornadoes have a tendency, well, tornadoes don't care about county boundaries or state boundaries, as a matter of fact. But notice that Jefferson County has a high of 96, 83 down here at Mobile, 90 at Baldwin, Tuscaloosa 73, 74 up in Madison County, Huntsville, Birmingham, Tuscaloosa, and the Gulf Coast area, all pretty good population centers. What's interesting is that, and again, I'm not picking on Coosa, but they have 17 recorded in Coosa County. Notice that around them, everybody is almost double Coosa County. I don't believe 17. That's not, the number's not right. The number is what we have in our records. But again, because of the population here, I don't believe that all the tornadoes are getting reported. As a matter of fact, if you look at Jefferson, I think this number is probably a lot more representative of all of North and Central Alabama, because we've had a huge population center. And one reason that population is so skewing this is, and we know this, is Cullman County up here stands out. They have a large number. Why do they have a large number? Again, Cullman County is not terribly big population. Yeah, it's sizable. But one of the reasons for this one up here is that Cullman County's had a very well-organized civil defense / EMA for a large number of years, from back in the late 60s and early 70s. So they've been very well organized. So what happens is they have more spotters, more reports, they put more emphasis on it, and I think their number in Jefferson and Tuscaloosa here are much more representative of all of us in Central Alabama. All right, we classify tornadoes in 3 groups: weak, strong, and violent, or the EF0 and EF1 for weak, EF2 and EF3 for strong, and EF4 and EF5 violent. I want to give you a piece of advice. If you're ever talking to somebody whose house has been damaged by a tornado, do not tell them that they had a weak tornado, okay? They do not take it kindly. There is something about your house has been hit by a tornado, you don't want to be told it's weak, because you think of your house as being pretty sturdy, and I understand that, so don't use that term. But we do classify them and give them names of weak, strong, and violent. All right, so what we're going to do is talk about the characteristics, and what I'm trying to do here is we're going to talk about one classification. We're going to give a sample picture and some characteristics. Now, this is a sample, okay? Not every EF0 and EF1 is going to look like this. All right? It's just one example. The good news here is 70% of all tornadoes fall into the weak category. So if you and I see one, chances are it's going to be a weak tornado. There's also good news here. We don't usually get a lot of tornado deaths out of weak tornadoes. The winds tend to be weak, the damage is a little bit less, and they don't usually kill. Lifetimes, 1 to 10 minutes. We just hit some bad news here. Why is that bad news? Well, it's bad news because with them being so short-lived, by the time a tornado forms, you or I see it, we get a phone call in or we radio in the information, the tornado may be lifting. So the Weather Service gets the report, they issue a warning, the tornado is already over. So the purpose of a warning is to give people lead time, and we just can't do it when tornadoes are short-lived. Since they're short-lived, the path lengths are going to be fairly short. Very interesting EF0 tornado in Marshall County back about 15, 18 years ago. It was on the ground for 9 miles. It's like, wow, 9, but the characteristic length is 3 of an EF0. Yes, but there are outliers. There's always that one. And while tornadoes are low pressure areas and generally rotate in a counterclockwise direction, there are a few, not many, that rotate the other direction in our hemisphere. So there's always something out there to be different. Wind speeds are on the order of 60 to 110 miles an hour on the Fujita scale or the enhanced Fujita scale. These are EF0s and EF1s, and I'll be happy to tell you that, well, I'm not happy to tell you, but these are the hardest to forecast. Why? They're hardest to forecast because the conditions that are present that allow a thunderstorm to produce a weak tornado are weak. They're hard to tell. You may have heard on the blog things like, well, we've got low CAPE and high shear. Okay, shear and CAPE, or CAPE is convectively available potential energy. Those are all indication, or CAPE is an indication of instability. If you have high CAPE and high shear, you have a pretty good environment. But when you have low on one and high on the other, it's not a clear-cut case. You're not always going to get them. There may be cases where you have in the sounding, you have an inversion. And it's like, okay, is that inversion strong enough to cut off the development of updrafts, or is the inversion weak enough that we will eventually break the inversion and thunderstorms will develop? So these are the hardest to forecast for. That means the hardest to issue watches for, the hardest to get warnings out well in advance. And well in advance is like 12 to 15 minutes. When you move up the scale, in the strong category, the bad news here is that about 28% of all tornadoes fall into this category, and they cause about 30% of all tornado deaths. Yeah, the number is down, but the number of fatalities is going up. Why? Because these are stronger, they're higher wind, more destruction. The lifetimes can last upwards of 20 minutes. Path lengths can be up to 15 miles. So if we have a tornado that's on the ground for 3 miles, can it be an EF3? Yep, it can. They can be short, but in general, they are not going to be short. They're going to be a little bit longer lived. Wind speeds on the order of 100 to 200 miles an hour, and on the enhanced Fujita scale, these are the EF2s and EF3s. And again, this is just an example. Forecasting is easier. Not always fabulous, but a whole lot easier because conditions that we look for, the shear, the instability, things like that, those things are going to be more identifiable, and therefore we're going to be able to get out watches and warnings usually a little bit better and give more lead time to people. When you get to the end of the scale, and by the way, this is the Piedmont tornado from March of 1994. Violent tornadoes account for only 2% of all tornadoes, so the number is significantly down. But in the United States, in a typical year, we will have 1,200 tornadoes. 2% of 1,200 is 24. So that means you can expect to have 24 tornadoes that are going to be in the violent category. So what happens is nearly all, or 70% of all tornado deaths are in the violent category. They can last upwards of an hour. Path lengths can be 50 miles, maybe even longer. If you listened to me back about 14 years ago, before I retired from the National Weather Service, you would have heard me tell you that we don't get too many tornadoes over about 80 miles. I'm revising that number because in the last 12 years, there's been a lot of tornadoes that have been over, in the vicinity of 100 and many over 100 miles. One of the first ones I noted was over in Arkansas, and the Arkansas National Weather Service office does a very good job of documenting. They documented a tornado some years ago that was on the ground for 123 miles. Continuous path of destruction from beginning to end. Forecasting is a whole lot likelier here because conditions that are present to allow a thunderstorm to produce a large tornado are going to be more identifiable. One of the reasons why we were able to start talking about severe weather a week ahead of April 27th was that the conditions just a week ahead, the models were giving us printouts of conditions that were definitely favoring severe weather. Did any meteorologist know a week ahead of time that we were going to have the magnitude of the event we had on April 27th? I don't think so. But we were talking about the risk for us having a fairly significant tornado outbreak, just not thinking 62 tornadoes in one day. All right. So let's talk about thunderstorms. We have to talk about thunderstorms because those are the parents to the tornado. So we have to know a little bit about thunderstorms. What does it take to make a thunderstorm? Well, the recipe includes moisture, instability, and some sort of lift. That is something to get air moving upward. Let's talk about these one at a time. First of all, moisture. We got to have enough. We need some moisture, but we really don't want too much. If the atmosphere is moist from the ground up to 40,000 feet, we're probably not going to get tornadoes because there's just too much moisture. What's going to happen is there's so much moisture that it's going to load down the thunderstorms, and they're going to be heavy rain producers, but they're just not going to produce tornadoes. We prefer, when we have moisture, that we have moisture in the lowest and there's no magic number here, 15, 16,000 feet or so. I mean, 18 would be okay. 12 would be okay. So we want the moisture to be in the lower and mid levels of the atmosphere. So again, we need, it's kind of like when you bake a cake. I've often asked my wife, well, why do we put a tablespoon of baking soda in? I mean, what does baking soda do to it? Just leave that tablespoon of baking soda out once, and the cake is what? Horrible. I mean, it's, I don't know what it does, but it does something to the recipe. So this is part of what we need in the recipe. When you get to instability, instability is the ability for air to accelerate upward. There's two parts to a thunderstorm, the updraft and the downdraft. The two parts, we got to have both of them. So we've got to get air moving upward. It's usually identified, or instability is usually identified by the rate of change of temperature with height. So the more rapidly the temperature changes with height, the more unstable the atmosphere is. A lot of times in the spring months, especially, and in the fall, and you may remember December of 2000, it was a very warm day. And in the spring, you get those days where all of a sudden the temperature shoots up and temperatures are approaching 80 degrees, and it's like, ooh, could be a severe weather day. And that's right, because we're getting a lot of warmth. We've also got the moisture to go with it. So, and the thing is, we look at oftentimes at temperatures around the ground and up to, say, 20,000 feet, the 500 millibar level. And when the rate of change of temperature with height is pretty large, then we can have well-developed updrafts. The source of lift, well, lift is an agent that lifts that moist, unstable air. So an example is afternoon heating. This is a summertime case where we get afternoon heating, and that helps to get the thunderstorms rolling. Summertime, you get up in the morning and you mow the grass in the morning and everything's fine, and by early afternoon you begin to get these puffy white clouds. You're beginning to develop some updrafts. By 3 o'clock you hear a little thunder, you get a shower, and then by 5 o'clock it's all gone. Well, that's afternoon heating is helping to create that lift. But there's other things. An approaching cold front will create lift because you have cold air invading warm air. The cold air is denser, so it will stay low forcing the warm air up over it. So you get lift from that. We also like to look for an upper level low pressure system that is off to the west, because to the southeast of that upper low, we also enhance the lift. So when you can combine afternoon heating and you can combine an approaching cold front, and you've got this upper level low, you've got a lot of ingredients that will support lift. How do we know about what's happening above the ground? Well, the balloon gets all the credit. We call it a weather balloon, but it doesn't do much of the work. It's actually the carrier. It's the vehicle that takes this little white box right here up into the atmosphere. And the balloon, the string, the parachute's there for safety. The box weighs about a pound, so when you get up to 80,000 feet and the balloon breaks and the box begins to fall, the terminal velocity is somewhere around 120 miles an hour. We do not want to have somebody killed by a falling radiosonde instrument, okay? We need the data, but we don't want to kill anybody, so the parachute is there to protect it. The parachute's also there. By the way, how many people have got your taxes done? Okay. 50% of you are in deep trouble because you've only got a week to go. Okay, the parachute is also a tax-saving measure, because the balloon, the string, the parachute, and the instrument are, and Kevin, is this right, about 900? About 900 bucks? Okay, and if it's less, tell me. I mean, or it's more, let me.
It's between 6 and 9.
Okay.
The newer instruments are a little cheaper.
Okay. So we have newer instruments that are a little less expensive. Well, that's great. All right. Even at $600, the upper air budget for the National Weather Service for a year is something in the vicinity of $54 million. Okay. So we have to have a lot of money. We launch 2 of these at the Shelby County Airport a day. There's 92 sites across the United States. So we've got to have this data. What does this give us? Well, it gives us pressure, temperature, humidity, and winds aloft by tracking it. So here's an example here. The red line is the temperature. The green line is the dew point. When the dew point and the red line, the temperature and the dew point, are close together, it's very humid. When they're very far apart, it's very dry. Remember, where did I say we want moisture? We want moisture down low. We don't have moisture down low. We actually have dry air down low. We have, at this level, around 600 millibars, which is, I don't know, I never can calculate it in my head, but 15,000 feet or so, maybe 12,000, 14,000 feet. We've got some clouds because we've got moisture there. And then from there on up, it's fairly moist. Now, the temperature decreases with height. And by the way, this diagram is called a skew T diagram. It's skew temperature, T for temperature. If you'll notice, like the 10 degrees centigrade, the line for 10 is over this way. It's at an angle. Okay, so the temperature is skewed, so it's called a skew T. Meteorologists are terribly creative when it comes to names. Here's another example. Red line is the temperature, green line is the dew point. They're close together down here, so up to about 700 millibars, about 10,000 feet, we have moisture. So we have moisture down low. We have what we want. Above, we have dry air. That's good. That will help with the development of updrafts. But we do have a problem. Right here to here, the temperature actually increases. This is an inversion, often referred to as, and don't get these mixed up, there's the cape and there's the cap, okay? The cape has an E on the end, but the cap is an inversion. What happens is, as air begins to rise, the air must maintain, if you imagine a little box that begins to rise down here at the ground, as long as the temperature within that box is to the right of this temperature line, it is going to stay warmer than the air around it. So, as long as the temperature of the box stays to the right, stays warmer than the atmosphere, the air around it, it will continue to rise. But look what happens. If I'm rising up like this, at this point, I now equal the temperature of the air, and then I get up here, and it's like, whoa, I'm colder than what the temperature of the environment is. So I can't rise anymore. I will actually fall back. So that's why this is called a cap. And oftentimes we'll have a cap, and when we have a cap, one of the things we have to try to forecast is, will the cap break? And in some cases, it will. In some cases, if it's a very strong cap, this is a fairly strong cap, but probably is breakable. So in a thunderstorm, we have two parts. We have the updraft, which is bringing warm, moist air into the storm. The warm, moist air is basically the energy supply. It's the gasoline. It's the fuel that is feeding the thunderstorm. What happens is warm, moist air comes in, and as it rises, that box of air will cool, but as long as it stays warmer than the air around it, it will continue to rise. But it does cool, and as it cools, at some point, the temperature and the dew point of that box will equal the same number. And when that happens, condensation occurs. So clouds form. Interesting thing happens when you have condensation. You release heat into the atmosphere. Not a lot of heat that you can put your hand on the side of our little box of air, but it's enough heat to help to keep the box of air warmer than the environment so it continues to rise. As more moisture comes in, more moist air, water droplets, condensation occurs, more water droplets form. The water droplets will rub and bounce together. Some of those two little tiny water droplets will touch, they'll stick, then you get moisture around them, and now we have a double-size water droplet. As water droplets continue to develop, they begin to get larger and larger, but as long as the updraft is an upward moving column moving at a pretty good rate of speed, it will keep these larger droplets up in the thunderstorm. At some point, some of these droplets will get large enough that they will begin to fall because gravity takes over. The air's not moving up strong enough to keep them up, so they begin to fall. When they begin to fall, the opposite of condensation occurs. Evaporation begins to occur as the water droplet begins to fall. Evaporation occurs around the edges of the water droplet. As that happens, that is a cooling process. And everybody here who has ever taken a shower has experienced that. Because you know when you cut that water off and you reach out for the towel and you get that little shiver, that's evaporative cooling. Your skin is trying to evaporate that water off of it, so it cools you, and you get that little shiver. So we've got evaporative cooling going on here, and so that makes the air denser, so it begins to fall, and we have the two components that we need to a thunderstorm. The updraft bringing warm, moist air into it, and the downdraft taking the cold, wet air out of it. Now, in most cases, on this side, the left side of the picture here, in most cases, the updraft will develop fairly straight up because the air as you go up doesn't change much in wind speed. Changes a little, but not enough to really interfere with the development, the straight up and down development of the updraft. So what often happens is the updraft develops, the downdraft develops up here and comes back through the updraft and it kills it off. In the spring, though, we don't have a wind pattern like this. We have a wind pattern like this. We'll have fairly strong wind above the ground, but as you go up, the wind gets stronger and stronger and stronger. So in this sheared environment, what happens is the updraft can't build straight up because as it does, it's encountering faster and faster air motion. So it tilts over, and then the downdraft occurs separate from the updraft. When you have that, you basically have the ingredients for a supercell storm. In addition to that, when you can get the updraft spinning, then rotating, you now have all the developments for the development of a mesocyclone. And that is, as this updraft begins to work its way upward, it begins to start spinning. And then underneath the rain-free base, you may see an isolated lowering called the wall cloud, which is going to be over in this area. Heavy rain is over here where the downdraft is occurring. Now, I'm going to talk a little bit about storm structure, and I thought I would try to intimidate you just a little bit. I was trying to update some slides, and I ran across a great diagram that has everything that's happening in a supercell thunderstorm. So I thought I would throw it into the slides and show it to you, and then we could talk about what's happening in a thunderstorm. So here it is. Yeah. I don't know. I decided that it wasn't such a good idea. Okay, so we're going to go to the one that's a little less complicated, all right? Now, all of these things are going on, but this one is a little easier to understand. When you're looking at a supercell thunderstorm, it depends on where you are relative to the supercell as to what you're going to see. So it depends on how close you are. Also, it's very important to know what direction you're looking. In this case, looking into the middle of the screen here, we're looking due west. That puts east behind us, north off to the right, and south, off to the left. So up high, if we're a long way from the supercell, up high we're going to see the anvil. This is the ice crystal clouds. This is the anvil level of the thunderstorm. It's very, very cold up here, on the order of minus 50 to minus 70 degrees centigrade, can be. We may see under the anvil, you may see mammatus clouds. These are pouchy clouds that represent turbulence at that elevation in the thunderstorm. They're not an indication of severe weather. As you approach the supercell, you may begin to see, as you get a little bit closer to it, you may be able to see the main storm towers. The main storm towers represent the updraft, which is right through here. So the updraft is tilted over because of the shear, the wind difference with height, as the wind, both direction and speed, especially the speed, gets stronger. So we've got our main updraft right here. When I showed this to my wife and was telling her about what it was, she said, oh, it kind of looks like cauliflower. And she's got a good point. The main storm towers may look a little bit like cauliflower. If you can see the updrafts, they're going to be very hard and crisp because the air is moving upward, and you can get wind speeds, upward motion, anywhere from 70 to 125 miles an hour, and that's upward motion. To the southwest, as you get closer now, to the southwest, you may see these developing towers. These are what's called the flanking line towers. Flanking line towers are new updrafts that are developing and moving into and helping to reinforce the main storm towers. Underneath the main storm tower, under the base of the main storm tower, we have what's called the rain-free base here. Here's another great example of us meteorologists. We're just not too creative. It's called a rain-free base because there's no rain falling here. Yeah. It's not called a snow-free base. It's called a rain-free base, all right? So it's a rain-free base because there's no rain falling here. Why? Because the air is coming into the bottom underneath the thunderstorm and rising up into the updraft. Now, air isn't only coming in at the ground and moving up. It's coming in at all elevations. But basically, at the bottom, the air is moving in and rising up. Underneath the rain-free base, you may get an isolated lowering. This is called a wall cloud. The wall cloud is generally under the most intense upward moving air, and condensation is occurring at a little bit lower altitude here. So you get this ragged, sometimes ragged looking cloud. To the north and northeast of the main storm towers, you have the downdraft. So this is where the heavy precipitation is occurring, and it is between the updraft and the downdraft that we get hail falling. So hail is going to fall in this area right in here. If you are in hail, you are near the most dangerous part of the thunderstorm. You're near that part of the thunderstorm where tornado formation is most likely to occur. Now we're going to slice through the thunderstorm, or go on top of it and look down. If we could take this helicopter and go way up high and look down, we would have this view. Previously, we were here looking back to the west. North is up, south is down, east is back over this way, and again, west over here. In the northeast quadrant of the thunderstorm, you have the heavy rain. This is where the downdraft is occurring, and we call this the forward flank downdraft. I want to mention that now because in the advanced session, we're going to talk about the rear flank downdraft, which we're not going to talk about this morning. We'll talk about that this afternoon. It's back here. But the forward flank downdraft is in here. The updraft is in this area, in the southwest quadrant. So if you kind of draw a line north-south, east-west, the northeast quadrant is dominated by the downdraft. The southwest quadrant is dominated by the updraft. You often get, as I mentioned, the hail falling between the downdraft and the updraft because the hail's heavy, so it's not going to fall way over here. It's going to fall closer to the edge of the updraft. To the southwest, we have our flanking line, and underneath the updraft, under the rain-free base area, is where tornadoes are most likely to occur, and typically they will come out of, but not always, a wall cloud. A wall cloud may be present. It may not be present. So, you can't, there's no absolutes. If you see a wall cloud, you've definitely got something. And if you see a wall cloud, you want to start looking for rotation in that wall cloud. All right, so again, we're going to position ourselves here in a minute, but what we're going to try to do is to give you examples of how a supercell looks at a distance. Supercells tend to be, but not always, isolated thunderstorms all by themselves. Here's an example of a supercell right here. We've got our anvil up here being blown into the screen. We've got the main storm towers in this area, but we're too far away to see any of the ground level features. Here's an example of a supercell. We've got the updraft in here. The updraft is primarily going off in this direction, but we often get some air that can move against the airflow, creating what's referred to as the back shear anvil here. But again, we can see the anvil being blown into the screen and the main storm towers, but we're too far away to see any of the characteristics near the ground. This is a great example of how supercells can be isolated. Here's supercell number 1. Here's supercell number 2. These two thunderstorms are outside each other's sphere of influence. So this supercell is not causing any problems for this one. This one is not causing any problems for that one. Here's the anvil for this one being blown into the screen. Here's the anvil for this one being blown into the screen. We can see the main storm towers. The main storm towers, we know where the updraft is, but again, we're too far apart, or we're too far away from these to see the ground level features on either one. There's an example of Humorous. Humorous can be very dramatic. Every place that you have a pouch, you basically have some downward moving air. Between the pouches, you have upward moving air. Pilot will avoid these because it's going to get very, very rough if you get under those. All right, remind you of the diagram, and what we're going to do is we're going to go through a series of slides that were made by a chase team out of Oklahoma University, or University of Oklahoma, and they were positioned in a location about here. They were too close to look at the big features, so they're close enough to see the ground level features. But before we do that, I want to show you an example of a supercell on radar, and this is from April 8th, 1998. And a lot of times, let me back up here, a lot of times people ask about the reference to the hook. You see the precipitation is wrapping around because we have the updraft rotating. That's the mesocyclone. So we have the updraft rotating and some of the rain is wrapping around. And indeed, this is what it looks like on radar. This is April 8th, 98. We're in western Jefferson County right here. We can see the wrapping around right here, so there's the hook. The mesocyclone is right in this area. If a tornado is occurring, and it is, right here is where it would be. Now, because of Doppler radar, we can also see how the water droplets, and that's what this is showing us, is just where the water droplets are and how big or how densely packed they are, the reds being more densely packed than the greens or the yellows. But we can also get velocities. And I'm sorry to go to a 4-panel, but it's just what I had available. But right here, this represents the image you just saw down low. This is the lowest velocity scan. The second one over here is above this one. The third one is above that one. And the fourth one is above the third one. So let's take the ground, or the near ground level one here. And what we have is we have pinks, which are high-speed air moving away from the radar. The radar is down here. And we have cyan or light blue moving towards the radar. So we basically have what we refer to as a velocity couplet. Now let me just mention something about Doppler radar. If I'm a Doppler radar, I can be anything I want to. I was a thunderstorm a little while ago. I'm a Doppler radar and I'm pointing my radar beam down this aisle right here, okay? I can tell motion away from me and towards me. However, if somebody is blowing wind across at a perpendicular angle to my radar beam at 1,000 miles an hour, I can see nothing. It's zero, okay? It has to be along the radar beam, either away from me or towards me. So we don't see, we really are not seeing but only two sides of the rotation. Now, it doesn't take a rocket scientist to figure out that we have outbound and inbound, that we have a rotation right here. And what I want to show on the 4-panel here is that at this elevation, we have a very good signature. We go up to the next elevation, we still have a good signature. We go up to the third one, we still have a good signature. We go up to the fourth one, we still have a good signature. So for a meteorologist, what this means is we have good vertical continuity. Do I know that a tornado is occurring? No, I don't. But based on the strength of the rotation, I have a pretty good idea there probably is one occurring. And as a matter of fact, this was an EF5 that occurred in western Jefferson County, part of Tuscaloosa County, and western Jefferson County, Concord area. It killed 32 people. All right, we're in the field. We're storm spotters. We're looking west. That's the middle of the screen. North is over here. South is over here. East is behind us. All right, over here to the north and northeast, we have the downdraft. This heavy rain is occurring. If any hail is falling, it's going to be right in this area. From here over to here, we basically have a rain-free base. There's no rain falling here. Can't see anything falling like we're seeing over here. From this point around to about there, we have kind of an isolated lowering. Now, it's a little broad. It's a little wide, but, it would bear watching. As a storm spotter, we would definitely want to be keeping our eye on it. Now, at least 20% of you have probably figured out that, we've already got a funnel cloud, so who cares about all that other stuff? No, you don't. What you have right here is some ragged clouds. We've got some ragged clouds here. Ragged clouds are a storm spotter's best friend because if there are ragged clouds under the wall cloud, they may help you to determine if there is rotation going on in the wall cloud. If rotation is going on here, then the updraft is rotating. And that means that on radar, the Weather Service meteorologists are probably seeing this rotation up here. But it may be weak rotation. They may think, well, maybe it's not producing a tornado. At this point, it is not producing a tornado. We advance just a couple minutes, and we've got our heavy rain to the north. We're still looking to the west. We've got our rain-free base right here. And now our wall cloud is a lot more concise. It's much more compacted, so I definitely would call it a wall cloud now. And remember that V-shaped cloud that we had right there, it is now right here. So it rotated from here around the east side from the south side around the east side to the north side of the wall cloud. All of these ragged clouds, scud clouds, all of those ragged clouds become helpful in determining whether or not rotation is occurring here. And now we have something that's beginning to develop. We have a cloud that is not just hanging there, it's actually descending. We define a funnel cloud as violently rotating column of air not in contact with the ground. And at this point, I'm pretty sure there's no contact with the ground here. The visible funnel certainly stops there. It may actually, the rotating air may go a little further, but at this point, it's definitely a funnel cloud. We're going to advance another minute or two, and we're going to, with the help of a telephoto lens, we're going to zoom in a little bit. We've got our heavy rain over here, and I don't know if you've been noticing, but it's been getting fuzzier behind the wall cloud. That's because the rain is wrapping around on the west side of the thunderstorm in response to the rotation of the updraft or the mesocyclone. We've got our wall cloud with lots of friendly scud clouds here that were helping to identify that rotation was occurring. And now we have, well, believe it or not, we have a tornado. There's a debris cloud at the ground. I know it's hard to see, so there's a connection here. Even though the visible funnel stops there, there is a connection to the ground, and we have debris, so this has now become a tornado. Tornadoes often start small. The visible funnel now goes all the way to the ground. At this point, we have a tornado. I now don't care about the rain, the hail, the wall cloud, or the rain-free base, okay? We've escalated. We're now DEFCON. Oh, I can't say that word in front of James. We're now at, no, I can say TORCON. No, I can't say TORCON. I can say DEFCON. We now have TORCON 46. I don't know, whatever. We now have a tornado, okay? So, bottom line is, we advance in time, and the tornado strengthens. It's now much stronger. We've got a tremendous debris cloud here, a nice condensational funnel. The wall cloud now is kind of fallen apart. Now, in the advanced session, I'm not going to show these slides again, but in the advanced session, we're going to talk about the rear flank downdraft, and this brightness that you see right here is an indication of the rear flank downdraft occurring. We've got the heavy rain, and again, it's wrapping around. So within a matter of time, the rain is wrapping around in response to this mesocyclone. So in a matter of time, the tornado goes away. Nope. It's actually right in here. But the rain is wrapped around. we get this a lot more in the southeastern U.S. This is actually in Oklahoma, but they get it too. Rain wrapping occurs a lot in the southeastern U.S. The April 27th, 2011, I observed the Tuscaloosa to Birmingham tornado in Jefferson County from Green Springs and I-65. It was not photogenic like it was in Tuscaloosa. In Tuscaloosa, the tornado was clearly visible. It was not rain-wrapped in Tuscaloosa. Somewhere between Tuscaloosa and Birmingham, it evolved and it became rain-wrapped. So what I saw from that vantage point on I-65, looking off to the west-northwest, was this huge, humongous cloud that was sitting on the ground. But because I knew to look for rotation, I could tell in that big, broad cloud on the ground, I could detect rotation going on in it. So I was not seeing the tornado, but I was seeing the rotation associated with the mesocyclone. The tornado was in the process of dissipating at that point, which I couldn't tell and I couldn't report because I couldn't see it because of the rain wrapping. But the chase team from OU that was on this storm, they got this shot, which is a very dramatic shot to be able to look down the damage path. The tornado has shrunk into the rope stage. It's off the ground. The visible funnel ends right here, but no damage was occurring at this point. So it has become basically a rope-like event, and it's a funnel cloud, and the event is essentially over, and you can see that it did a great deal of damage here at this. So this was a baseball park. There was a concession stand right here and, baseball fields and that sort of stuff. All right. Now what I'd like to do, and I know we have a large audience, so it's hard to do this, but what I'd like to do is to give you the opportunity to practice in a safe environment, okay? We're in a very safe environment here. So we're the storm spotter photographer. We're taking this picture. So the question I want you to answer or to try to figure out is, what direction are you as the photographer looking? So what you have to do is you have to figure out some things. So let's figure out some things. First of all, you've got a title over here, so I'm giving you a clue. It's a rain-free base, okay? So there's the rain-free base right there, all right? What's this over here? Rain, yeah, heavy rain, all right? What's this here where we've got 1, 2, 3, 4? What's that? Flanking line, yes, okay. And flanking lines usually extend to the southwest. So what direction are we looking? South, yeah, south, okay. And listen, trust me. Directions can always be difficult. It's tough. I get inside a building like this. I don't know whether that's north or this is north. I don't know what direction is which. And it's hard to tell on these, okay? But the reason that I know is because I have the notes from the photographers and I know exactly what direction they were looking. So I do have the answer key, if you will, all right? So don't feel bad if you don't get them right, get them all right, all right? Don't feel bad. The purpose here is to try to give you some exposure to what you may be looking at, all right? And this is only one small view. A lot of times when you're traveling, you have a GPS or you have some sort of compass and you know what direction or it's in your backyard, you know what directions are which directions, So, okay, there's one, rain-free base. Let's take another rain-free base. Here's the rain-free base, all right? What's this over here? Rain, heavy rain. Now on this one, we actually can see right here, there's some blue sky here, we can actually see the edge of the main storm tower. So the main storm tower is in here, so the rain-free base is here. And there's 1, 2, and there may be another one, but it's kind of washed out, it's hard to see. We've got the flanking line that extends off to the southwest. So what direction are we looking in the middle? Okay, I heard northwest. I'll accept northwest. You're generally looking to the west in the middle here. So with the heavy rain off to the north, so that puts the north over this way, puts south where the flanking line extends to the southwest, so we're basically looking west. Now, what's that? If you go to the Galleria and ask 100 people, and you show them this picture, 99 out of 100 will probably tell you that that is a tornado. Why? Because it has the shape. Okay, it has the classic shape. Now, once again, I have the cliff notes on this. So, The photographer noted that, yes, it has the shape. Now, here's something else that is important to note. If you reported this as a tornado, what's overhead? The main updraft. If there's a mesocyclone, the guy at the National Weather Service who's looking at radar, if he's seeing a rotation in here and you report a tornado right here, he's got two elements. He's probably going to hit the button for a tornado warning. But what the photographer said was there was absolutely no rotation in any of this. As a matter of fact, you could actually tell that this was a little bit of rain falling. Now, there shouldn't be any rain in here because it's the rain-free base. But for some reason, for whatever the reason, there is just a tiny bit, and this is an example of what can fool you. And believe me, I've been a meteorologist for coming up on 50 years come June 1st, and I've seen a lot of things that were like, holy mackerel, could that be? It's like, well, I better watch it. So you may sometimes want to hold off making a report instantaneously to observe something to tell whether or not it is what you think it is initially. So you need to confirm what's going on. All right, let's take another one. It's a rain-free base. This one's a little harder. What direction are you and I as a photographer looking? What's into the screen? Up. Oh, throw that man out. Okay, the rain-free base is overhead, okay? What's this up here? Heavy rain. So we're looking to the north or maybe even a little northwest. The rain-free base is overhead. The thing is, if you have a rain-free base off to your west and it moves over you, it's going to look different. Thunderstorms are dynamic. They're not sitting still in both space and time. They're moving and they're changing. So you're going to have to be aware that even if you're at a good location right here, it may be overhead, so it's going to look different. All right, now we're going to move up to wall clouds. So we've got a wall cloud right here, all right? What's this back here? The rain. What direction are we looking? North, absolutely. We're looking north. Or if you wanted to say northeast, I accept northeast, that's fine. Here's the wall cloud. Now, it's a still photograph. Do you get the sense of circular activity in here? Yes. And you are absolutely correct. The photographer noted that all of these ragged clouds here made the rotation of this wall cloud clearly visible. We have a rotating wall cloud. That means above us, we have a mesocyclone. We have the potential for a tornado to occur. Doesn't mean that one will occur. In the case of April 27th, the storm got out of Walker County. I'm sorry, the National Weather Service in Birmingham got a false alarm, technically. They issued the warning because there was a wolf in the woods, okay? There was something there. It just didn't happen to touch down till it got into Coleman County. All right, we're still looking at wall clouds. Here's a wall cloud right here. What's this? The rain, right. We've got our rain-free base. We've got our wall cloud. This wall cloud has a little something extra. It has a beaver's tail. Interesting thing that's happening here with the beaver's tail. The rain area is up here, so this air is cool and wet. So the air is feeding back, and we've got a cloud, a cloud, a cloud, a cloud, a cloud, and then a string of clouds. What's happening is this air is actually feeding right back and into the updraft. So we get a beaver's tail. Do you and I in the southeastern U.S. want to worry about that? No, we don't. You may see it, you may not see it, okay? But it's something that might be there. So what direction are we looking? West, absolutely, okay. Now, this one is tough. I actually took this photograph. This is in Alabama. I will give you a clue, all right? I'm not going to point out anything. I will give you a clue. The road is what? Okay, it's wet. The rain is now over here. All right? So what direction are you looking? South, absolutely. Now, I'll give you another fact. If I could put this in motion, which I can't, you see these ragged clouds? They were coming out of the screen. You see these ragged clouds? They were moving into the screen. There was rotation going on here. There was indeed a mesocyclone. Why did my office at the time, which is directly behind us by about a mile, why did they not issue a tornado warning? Storm spotter reports, because the Montevallo Police Department had been helping watch this, and it produced no visible funnels, despite the fact that it was rotating. So the National Weather Service guy on duty he was poised to issue a tornado warning at any point, but it was right after this that the whole mesocyclone fell apart, the wall cloud disappeared. So once again, storm spotter reports become crucial because they give the meteorologist information about what's happening at the ground, even when there's no information, when nothing is happening. So sometimes a no report can be very, very good. All right, now we're going to look at a couple of things here. I want you to determine, we're not going to worry about direction. I want you to determine whether this is a tornado or a funnel cloud. Funnel cloud? Who said can't tell? Who said can't tell? Okay, you are absolutely right. Go to the head of the class. You're absolutely right. You can't tell. Why can't you tell? Because we've got trees, bushes in the foreground. We've got definitely, and all these ragged clouds here, man, you could see the rotation. But does it extend to the ground? I don't know. So what do you report? You got to report something because you've got something. You've definitely got something, whether it's a funnel cloud or a tornado. So this is where meteorologists are very understanding. We, in the meteorological profession, have had great sensitivity training to uncertainty. Every time we issue a forecast, the 7-day forecast, I want to tell you, that 7th day, we're pretty uncertain about that, okay? All right, so we understand uncertainty, but you do need to report. What do you report? You report, I have what appears to be a funnel cloud, but honestly, there are trees or hills or whatever between me and it, and I can't tell if it extends to the ground. Now, if it extended to the ground, there's a possibility that you might see debris. You might not, okay? When I caught the Cordova storm on April 27th, one of my first indications that the chase was about to be successful was as we were driving eastward on I-22, we began to see out of the sky to our south, to our right, we began to see pieces of the ends of limbs. I don't mean, long branches. I mean, a cluster of leaves, like at the end of a branch where there's 2 or 3 clusters or things sticking out that were ripped off with rotating wind. And that was our first indication that there was definitely something going on. As we got a little further to the east, we looked back to the southwest, and there it was. All right, here's another one, tornado or funnel? Well, I heard tornado and I heard funnel. I heard more funnels than I heard tornado. Actually, it's a funnel. But I'm glad you said tornado. The visible funnel or the condensation funnel stops right there, but we can see the horizon. There's no debris. Does the rotating air stop here, or here, or here, or here? I don't know, and it doesn't matter. It stops above the ground. There's no debris down here. So your report would be, I have a funnel cloud. All right. Probably wouldn't take much longer from this, and you probably would have a tornado, but you don't have one right now. What about this one? Okay, yeah. All right, see, I'm not a bad teacher. I just throw in an easy one once in a while. Yes, tornado. Look at the debris that's being thrown up here and the debris that's being thrown out this way. Remember, around a tornado or a wall cloud, you may get the sense of stillness. As a matter of fact, one of the things that I hear reported a lot are people say, you've heard the phrase, I'm sure, the calm before the storm. Well, a lot of people report just before a tornado strikes that it's very calm. And there's a really good reason for that, because if you stop and think about it, the air is coming into and rising up. So right above your heads, not far up, there's probably a great deal of violence going on in terms of high wind speed. But down where we are, our 6 feet or 7 feet or whatever of the atmosphere here, it's likely to appear very, very calm. Tornado or funnel? Okay, I've heard all the key words I want to hear. I've heard tornado, you can't tell. Well, you sort of can, but I mean, I could understand where you might say you couldn't. And I've heard the word debris, because this tornado right here, and it is a tornado because it's got debris. So it's got debris, which primarily is, and this is late December in north central Texas, it's primarily grass and leaves, okay? All right, but just to give you an idea of what we're asking you to do, this is how it looked about 2 minutes later. Now, all of that debris is now a condensation funnel, okay? So we go from debris to condensation, all right? So it makes your job as a spotter is very difficult. All right, tornado or funnel? Right, tornado. But as a storm spotter, do you have something to be worried about? Yes, this. What's this? It's rain. But what's it going to do? If you have a tornado, you have a mesocyclone, you have rotation, it's going to what? Wrap around. And it did. There's the tornado. Here's the rain wrapping around. All right? So your job is very, very difficult. You've seen this one already. This is such a wonderful picture. The gentleman who took this was on the U.S. highway. You can't see it, but there's a U.S. highway right here. This is in eastern Arkansas. This tornado was on the ground for 60 consecutive miles. What's interesting is it was just to the south of Jonesboro, Arkansas, and it never crossed the city limits of Jonesboro once. It never actually entered the city limits of Jonesboro. Jonesboro, the city of Jonesboro, suffered $20 million in property damage. Got any idea why? Hail. Yep. Because the tornado was to the south of the city, but what was just to the north was where the hail was falling, and there was $20 million in damage. This stayed mostly in a very rural area. We've got our wall cloud, we've got our beaver's tail, we've got our condensation funnel, we've got our debris funnel, and if the photographer had panned over here just a little bit, you would see clear blue sky. Actually, there's another thing you would see too, and this is the part that always scares me is, and he did pan over this way, but he wouldn't let me have that picture. When he panned over this way on the U.S. highway, there was a very large yellow and black school bus. Scares the heck out of me when I think about a tornado being that close to where a school bus was, even though it's moving this way. It scares me when I think about that. All right. This is an Alabama tornado, actually, Cottondale. Anybody remember the tornado that occurred in Tuscaloosa County and affected Cottondale, and it heavily damaged a Food World and threw a car from the parking lot into the Food World? Remember that? Okay, getting a few hands there. Well, this is that tornado. Well, let me back up. Is it a tornado or not? Absolutely. You guys are great. You all moved to the head of the class. Can't tell. Right. We have a problem. Houston, we have a problem. We have trees. It's a problem. I want you to notice something here is that we have a little clearing. Well, it's a minor clearing in the trees, a weak spot in the trees. I also want you to look back this way. In the next picture, notice that there's blue sky back here. Okay, and here's our gap. Is it a tornado? It's maybe. Yeah, I would say maybe. This is a good maybe. And then it moves into that gap. And it's like, yes, but look at the blue sky. And yet it was very, very dark under this. The light wasn't getting into us just yet. Okay, tornado saved. Oh, by the way, I want to tell you something about, I want to tell you something about this. In my career in the National Weather Service, I surveyed a large number of tornado and severe weather events. And on only 2 occasions was I denied access to the damage. One was Pelham, Alabama, and the other was Cottondale. The security for Food World would not allow me into the Food World building. And I wanted so bad to get in there because I had already flown over in the Tuscaloosa EMA's helicopter, and I already knew the damage and the path, but I wanted to get in because I wanted to get pictures of how far the car had gone through the roof. And the security guy, they would not. And I didn't want to get arrested. I wanted the pictures, but I didn't want to get arrested. So I accepted the no. I don't accept no's very often, but I accepted that no. However, it's interesting how things work out. About 6 months later, I was giving a safety weather talk at Reform, Alabama. And a gentleman in the audience came up to me afterward and he said, by the way, you remember the Cottondale tornado a few months ago? I said, yes. He said, I was in there when the car came through the roof. And I said, "You were? That's wonderful. You have to tell me what happened. I've been dying to know what happened." He was one aisle away from where the car came through the roof. But interestingly enough, the car didn't make it to the floor. When it came through the roof, it came through all the electrical cables and conduits and all the things that are in a roof, and they helped keep the car about 6 feet off the floor. So the car was sticking through the roof, but it didn't get to the floor. And he said what they did is they just knelt down, in the aisle they were in. They knelt down, and of course they had all the shelves around them that would protect them from things coming in from the top. And indeed, it protected them from the car. So I did get to find out, despite the fact that those ninnies at Food World wouldn't let me in. All right. No, I'm sorry. I need to use James' term, those jabronis. Yeah. Okay. We need you to know what to do to be safe. There's 2 rules. Get as low as you possibly can. Put as many walls between yourself and the outside. Now, the audience here is a wide variety of ages. So many of you may have heard the rule about opening windows. Okay? Do a brain fusing right now and forget that rule. Don't worry about windows, okay? Yes, a tornado is a low-pressure area, and as it approaches a building, we used to think that if the pressure built up inside the house, that it could cause the building to explode. Well, that's not true. Engineers and architects have helped meteorologists figure out that there's enough air leaks around the windows and doors and the foundation and the roof line that a building can basically equalize air pressure on its own. And you're risking your life if you go to a window, because if debris around that tornado breaks that window while you're trying to open it, you could be injured or killed by flying debris. So the bottom line is, forget windows. Avoid upper floors, get to the ground floor. In this case, this house does not have a basement. So the family here that lived here decided on a closet that was below the stairway that led upstairs for their safe shelter. And then once you're, once you're on the lowest floor, put as many walls between yourself and the outside. And that closet was under the stairwell at the middle of the house, so they were walls of the closet were to other parts of the structure. This is what the house looked like before it was hit. This is what it looked like after it was hit. There's no safe place to seek shelter up here, unless you're one of those people that likes to hug the commode, and then, I don't know, it's debatable whether there's a safe place up here or not, but the commode was still there. Okay, but there's no walls up here. There's no combination of walls to protect you. You can see it didn't do any good to open windows, and again, the family had gone to the closet below the stairway. This is a good example here of not being in a vehicle. There is a great deal of controversy in the meteorological enterprise as to what you should do in a vehicle. I guess I'm a little old school, and I'm inclined to get out of the vehicle because I've seen too many times where vehicles have been thrown literally hundreds of yards, and if you were in the vehicle, there's no way on God's green earth that you would have survived. I've seen too many of those. I got into a bit of a trouble with got into an argument with a professor from Kent State. This jabroni came down after the March 27th, 94 event, 2 weeks after it, and he went surveying around North Alabama and North Georgia, and what he observed is a number of destroyed mobile homes with cars in the driveway. Okay. What does that mean? Well, what it meant to him was the people in the mobile homes should go into the cars because the cars were still there. Wait a minute. Were those cars there 2 weeks ago? He had no idea. And then to add insult to injury, he said, well, you should get in a car because cars have airbags. Okay. Cars have airbags. And you know what? If you don't turn on the ignition, the airbags don't deploy. Excuse me. Do not stay in a vehicle. Now, if you're a very intelligent person who's been to spotter training, then you have more average intelligence than the average public. So what you can do is when you see or observe a tornado, you need to determine what direction the tornado is moving. How do you do that? Well, you stop and you figure out, is it getting smaller? If it's getting smaller, chances are it's moving away from you, okay? If it's staying the same, it's probably moving left or right across your field of view. If it's getting larger, it's probably moving at you. If it's moving at you, you need to seek shelter. Now, I'm going to tell you that in Alabama, we do not put roads on a grid like they do in Oklahoma, Texas, Kansas. Okay, there's no grid work. We have hills. We have more rivers. So we have problems. Roads don't go in straight lines. So I think the best thing you can do is if you're in a vehicle and you're pretty sure the tornado is approaching you, then you need to get out of the vehicle and get into a ditch or depression, something to put your body below ground level to be absolutely the safest. Now, I have some evidence to back that up. There was a gentleman who was severely injured who did not make it to the basement door of a house in the Piedmont tornado, just a half a mile from the Goshen United Methodist Church. He was actually, his family had gotten into the house, but he was approaching it from across the street, and he didn't quite make it. And the wind picked him up and threw him across, and he was a half a mile out in the field. And he had several injuries, broken bones and whatever, but he survived. I do believe that you stand a better chance than being in a vehicle because you can see that the glass is all gone here. Most of this glass was inside the vehicle. You'd have been ripped to shreds, okay? Another thing is mobile homes, and in mobile homes you have to do something different. When the tornado watch is issued, you need to go someplace else. Mobile homes are not safe. And me and the Mobile Home Association, we have words on occasion. And one of the words is that you need to do something different in mobile homes, despite the fact that they're tied down. And being tied down is wonderful. But unfortunately, mobile homes still come apart. As a matter of fact, I know exactly what speed that they come apart. If you drive down any interstate in Birmingham, you can watch mobile homes go driving down the road coming apart at 70 miles an hour. All right, what to report? We want you to report tornadoes, funnel clouds as well. And if you don't know, don't worry. Report what you think you see and let the uncertainty be part of your report. We want to know about hail, preferably half-inch or bigger. When it's small hail, we tend to get a lot of small hail events, and those don't do much damage, so we're really not too interested in those, but half-inch or larger. And when you report the bigger stuff, report it relative to well-known sizes like quarters, 50-cent pieces, I won't say hen eggs, okay? But baseball, ping pong ball, those sorts of things. We want to know about wind damage. Don't try to figure out if it was a tornado or straight line wind. Just report the damage that has occurred. And that brings up another point. When you make a report, be sure to make your report accurately. Before I left the National Weather Service, we had an event in northern Tuscaloosa County, just north of Northport. On US 43, there was a subdivision up there, and the report that came to EMA, that EMA relayed to us, was that the houses in that subdivision had, now listen to this very carefully and picture in your mind the damage. They had significant roof damage. Okay? Wow. Is that, I don't know about you, but that's pretty bad, right? Significant roof damage. That was the exact quote. So the next day, as part of my job, I went up to survey the damage. The worst damage I could find anywhere was 13 missing shingles. Now, 13 missing shingles does not equal significant roof damage, okay? We want to know about flooding or flash flooding. If you know how much rain has fallen, that really helps. So if you have a rain gauge, that really helps. Where do you report? We want you to report to the National Weather Service, local law enforcement, local emergency management, local media outlets, radio or television stations, and we hope you'll be part of the ABC Skywatcher group. And 911 is your last choice. Please report to 911 only when you have something that involves life, risk to life, okay? Because 911 doesn't need to be bombarded with all these reports of a tornado unless you're reporting some damage. Now, when you report, if you really want James Spann to know exactly where you are and where the event is, just reference the nearest barbecue joint. And he's got it. All right. Okay. Whoops. Let me back up. I'm sorry. I forgot that okay. Now comes the video part. All right. These are videos that were made by storm chasers and others, many of them just accidentally, because now that we have phones and cameras on our hips, we basically have a camera available all the time, so we're getting a lot more videos, which are wonderful for adding to training. what I want you to concentrate on here is primarily the presence of the rotation. The still pictures you've seen, in many cases, I know the history, we know rotation was going on, but I can't really show you that. In this, the purpose here is to indoctrinate you to rotation. So look for rotation, especially near the ground or actually up in the funnel or at the cloud base. All right, so here's the tornado. This storm chaser, Andy Gabrielson, is entirely too close, but he gets some great video, so. And it's crossing the road. By the way, the power flashes, those are not transformers exploding. What they are when power lines, because of the rapid wind, the power lines are getting close together and arcing. So that's what's causing the flashing. That can be a help at night if you can't see the tornado. There's the tornado right there. And again, look at the rotation. You can see some debris. There's debris down in here. You can see that debris. All right? Now, this is another example. This is an impromptu example. This is not a storm chaser. He just happens to be right here, and here's the tornado coming down. Is it a tornado? Can't tell. Yes. Okay. Now, I'm basically pretty sure it probably is, but we can be really sure. Right. Watch for it. Well, I thought this one had debris, but I thought there was some bigger pieces of debris. Oh, well. Okay. The other thing I would ask you is if you take video, hold the camera still. Just a suggestion, okay? I imagine he was pretty excited. All right.
Now you can hear it. Now you can hear it. Just tore up a house, I think. That's not good. That is not good.
Yeah. People who are videotaping tornadoes have a tendency to say some very interesting things, which is why I don't usually play the audio, because you might hear a storm chaser say something like, well, gall darn.
See it right there? It's going to pass your house, sir.
Condensation occurring out here on the side. Looks like we almost have a second spin up right there. Probably do, actually. A lot of times tornadoes can be multiple vortex. That is, there's more than one rotation in there.
So powerful. Yep. That is, God, that's...
You can see up here, these clouds are feeding into the picture. So there's good rotation. So if there was a wall cloud with this, and I don't know if there was, it was probably rotating. All right, we'll move on to an English storm chaser, Stuart Robertson. He has had more luck than I have. But look at all the debris. And I think this is primarily, I think it may be going over a fairly large lake because we're getting a lot of debris, and yet it's pretty light. So it's probably just water. But you can see the rotation that's here, and of course you can see it up high. And then we begin to, I think it gets off of the lake here, and notice we begin to get some debris. And look at, and this is fairly light debris, but look at the debris, and you can see it actually climbing, and then some of it falling out as it gets over here where the wind speed is less. There's a fairly sizable debris. If you really want to see probably the champion of all debris-producing tornadoes, do a YouTube search for Pampa, Texas tornado. There is some fascinating video taken of that particular tornado. Oh yeah, and just drive by and don't pay attention to what's going on here. There's fabulous video of the Pampa, Texas tornado, in which in one frame of the video there are 5 automobiles aloft at one point. All right, and now here's one that's pretty interesting because there is no condensation funnel. But what have we got here? Debris, yes. All right, now he's going to zoom out a little bit, or back out a little bit, and you're going to actually see the condensation funnel up aloft. All right, there's the condensation funnel. But it stops right here, and there's a connection down to the ground. and we've got rotation going on here. And we can see it in all this debris. Now he's going to change vantage points here and zoom in. I want you to watch right here. He's going to zoom in a minute. There's a house right here. Pay close attention to this house right here.
Look at the house.
Oh, that's nothing.
The house is coming apart.
No lie, Sherlock.
Oh my God. Did you see that?
No, we missed the whole thing. Let's back up and play it again. Okay. After I saw this video, I went to my boss and I said, the next time I go out on a storm survey looking at tornado damage, I want you to remember this picture here. But that's why we used to think houses exploded, because what's happening there is it is the force of the wind against the structure, and suddenly the structure fails because of the force of the wind. And when it fails dramatically. And the whole house failed simultaneously, which would give you the impression that it exploded, and it did not explode. Okay, last item here is, and I'm sorry, don't write this down. Don't write this down. It's wrong. Okay, I can't remember what it is. I'm sorry, I switched presentations. I had it updated, and I switched presentations and forgot about this. But I'll put it into this afternoon. They've got a new name for it. It's I think almost everything is right except it's OS brochures, and then it's something like I can't remember, SG June 6-11.pdf or something like that. I'll have it this afternoon. It's a large group. Do we have time for a couple of questions? I don't know what the time is. Oh, well, thank you. 2 questions. Okay. Get out of here. Okay, anybody have a couple of questions? Yes.
Why does the air when the sky kind of appear to be green just before it turns?
That's a very good question. Green appears primarily because of the refraction of the sunlight in the cloud through primarily, but not always restricted to, hail. Oh, I'm sorry. Yeah, she asked why is it that the air sometimes looks, the clouds look green before you have severe weather. And the reason that it looks green is that the green color is refracted through hail. So thunderstorms that have hail, basically the sunlight in the tops gets refracted and you see the clouds take on a greenish or greenish yellow appearance. Now, recent research has suggested that doesn't only happen with hail, it also happens with the larger raindrops. So you may have hail. The cases that I personally know about where the sky had some green, yellow to it, there was hail involved, okay, with those cases. But research is saying that also hail plus large raindrops may lead to refraction of the green color.
I just noticed it was green every time I was near a tornado.
Well, and most supercells that produce tornadoes probably have hail. It's kind of like we're interested in the wind damage and wind. We're interested in the hail, but when you get to a tornado, we don't care about all those other ones. We just care. On March 27th, 1994, the Piedmont tornado was on the ground 50 miles in Alabama and 3 in Georgia before it dissipated. And we got to all those tornado reports. There were hardly any reports of hail, and yet I know that storm produced a lot of hail. But once again, once you get to a tornado, we don't care about the hail so much. So, one more? Yes.
Earlier when you were doing the anvil cloud, isn't that a cumulonimbus cloud?
Absolutely. Give that gentleman an A. Very good. All right.